Hello class, I am Simkho Shaulov, and this is the series Elastic Actuation and Quasi-Direct Drive Actuation and Comparison Final Project. And so we're going to start with our takeaways from Professor House's class. And we learned from this class about the field of mechatronics, we learned about soft robots, we learned about actuators, and we learned about bandwidth and backdrivability. And so the field of mechatronics is really where the TAs and Professor House to stimulate our knowledge of robotics and open our minds up to new possibilities of engineering that we did not know of before this course. And the development of soft robotics is just a better alternative to traditional rigid body robots and prosthetics. And we learn what an actuator is inside of a system, where it's just the main mover that helps the system move, and it is measured by bandwidth and backdrivability. And so bandwidth and backdrivability are really just measures of how fast the system responds to a changing input and the frequency, which can be taken in a closed loop amplitude, where it reaches -3 decibels is said to be the bandwidth of the system. And the backdrivability is the level of easiness of transmission or how easily a human can interact with the system. And so we have series elastic actuators and quasi-direct drive actuators, which series elastic actuators are, they have small torque motors, they have big gear ratios, and they have an elastic element, which means that they will have low bandwidths and they have medium to low backdrivabilities. And we have quasi-direct drive actuators, which have high torque motors and low gear ratios, which means that they'll have high bandwidths and high backdrivabilities or low torque resistances. And so we have, to represent an actuation system in real life, we must model it. And so this hip exoskeleton modeling is composed of an electrical part, a mechanical part, a transmission, and a wearable structure. And here's the parameters we're going to use to derive the equations for backdrivability and bandwidth. And so we start with the equations for the electrical part, which come from Ohm's law and the back EMF relations. And we have the mechanical part, which comes from the sum of the torques. We have the transmission, which contains the movement equation with damping and stiffness coefficients. We have the wearable structure, which contains the equation in relation to human thigh movement and assisted torques. These equations are all in the time domain, however, we need them in the frequency domain. So we're going to perform the Laplace transform, and we're going to get these equations here, and we're going to use the initial conditions plus some arithmetic, some plugging in equations to solve for our bandwidth and our backdrivability, where bandwidth is just the output signal torque over the input signal torque, which accounts for the PID controls too, and this gives us the bandwidth. And then we have to solve for our output signal torque and divide by the human interaction input angle, and then that gives us our backdrivability. And so here is the control block diagram from Simulink, and it starts off with an input signal chirp function through a gain, and then onto the PID control. This tells the system what to do. The saturation comes in as a voltage, but the 1 over Ls plus R block turns it into a current for the next saturation. This goes into the motor mechanical component through a torque constant gain, where it passes through the 1 over JMS plus BM block, which acts as a transmission and turns the signal into an angle rate that passes through the gear gain into a torque sensor, where the angle rate turns into an angle output with the stiffness and damping coefficients gains being accounted for, which is finally outputted and corrected by the other parameters. And this is stored as data and then plotted on a graph. And here we have the control block diagram for backdrivability. It starts off the same way with an input chirp function and an initial gain of 0 volts. And so the initial signal passes through our saturation and voltage and turns into a current. And through the 1 over LS plus R block, the current passes a gain of a torque constant and turns into a torque signal. The 1 over JMS plus BM block turns it into an angle rate response and time domain, which passes through the integrator to become an angle response. The response passes through the gear gain and takes into account the stiffness, the damping coefficient gains before being outputted from the transmission to an actual torque. And the input chirp function here is 0 to 1 hertz, which is with an amplitude of 5 degrees. And 0.87 is just 5 degrees in radian form. So that's where that comes from. And here we have our given parameters for the simulation. And here we have our simulation graph for bandwidth. And for the SEA and QDD, I used the PID values of 145 and 3.5 respectively. And the SEA bandwidth was taken at the -3 decibels line, which is about 4.97 hertz. And the QDD bandwidth was taken at the same line at about 111.1 hertz. And here we have a simulation graph for backdrivability, where the backdrivability is taken at the peak of the height of the first peak, and SCA backdrivability comes out to be 15.34 Newton meters, and QDD backdrivability comes out to be 3.529 Newton meters. And here we have a final comparison to some of the results. The SCA has lower bandwidth and takes longer to process signals due to the higher gear ratio and medium torque resistance, so it's compliant with human interaction. But QDD has higher bandwidth due to the lower gear ratio, which means faster processing, and higher backdrivability, which means there's a low resistive torque, so it is highly compliant with human interaction. Thank you.